Hi everyone, welcome to the Internship Studios session on serverless offerings from AWS. So in our case, we'll be discussing in this session about AWS Lambda. So actually it is very important for cloud and DevOps prospective professionals to understand the serverless offerings nowadays because organizations are moving from managing their own servers to just uh, and looking to move towards faster go to market strategies due to the availability of this managed services. So what these are helping us to do is they are helping us to ship our code faster without managing or worrying about the underlying infrastructure beneath. So everything is managed in the backend by the respective cloud platform provider, and we just need to be concerned with our business logic. So it will be an interesting one. So we'll just go ahead and understand the basics first. So this is a very interesting graph that I have taken. We can see the upper arrow in the left side has increasing focus on business logic. Business logic means the source code, the application source code. And in the right side, which is a straight arrow, we can see decreasing concern and control over stack implementation. So initially we can say this is the graph that went. So initially it was the bare metal, then we had the virtual machines, next we had the containers, and now we have the functions. So the evolution of IT structure from bare metals to serverless functions nowadays has been a very fascinating journey. So this transformation from the traditional bare metal setups, bare metal means the physical servers, to the modern paradigm of serverless computing. So this progression has not only enhanced the efficiency of IT operations but has also opened up new avenues for scalability, flexibility, and resource optimization. So, in this comprehensive exploration, we'll delve into the key milestones that mark the evolution of IT infrastructure. So, initially, we had the bare metal servers. As in the left side, we can see this. These are the served up racks, right? We have the bare metals. So, the inception of IT infrastructure can be traced back to the era of bare metal servers, where physical hardware formed the backbone of computing environments. So, organizations would invest in dedicated servers, each with its own operating system and applications. While this approach provided very raw computational power, it suffered from challenges such as very limited scalability, resource inefficiency, and lengthy deployment times. So, as demands grew, the need for a more agile and scalable infrastructure became apparent. So, then with that need came the concept of virtual machines. So, the advent of virtualization marked a very significant milestone in the IT evolution. So, virtual machines emerged as solution to the limitations of bare metal servers. Hypervisors enabled the creation of multiple virtual instances on a single physical server, each running its own operating system and applications. So this technology, what it did, it allowed for very better resource utilization. So it also improved scalability and it increased flexibility as well. However, these virtual machines, they also brought some challenges like increased overhead due to the duplication of operating systems and slower boot times. So they were very slow to switch on, exactly you can say, and the application to come up in those servers. So after that we had the concept of the containers. So containers which have been popularized by current technologies. So you have been heard like tools like Docker, So they introduced a very lightweight and portable solution to the challenges posed by virtual machines. So unlike VMs, containers share the host operating system's kernel, as we already know. So resulting in faster startup times and reduced resource overhead. Containers also encapsulate applications and their dependencies, providing a very consistent environment across different deployment stages. So this approach what it did, it fostered the rise of microservices architectures, enabling organizations to develop, deploy and scale applications more efficiently. So finally we had this serverless computing. So here we have mentioned it as functions. So the latest leap, a giant leap we can say in IT infrastructure evolution is the rise of serverless computing. So where developers, you already know roles, right? SD, software development engineer, who write the application code actually. So they can focus solely on writing the application code without the need to manage underlying infrastructure. So they don't care about on which platform my application is hosted. Just they want their application to run. That's it. So serverless platforms such as AWS Lambda and in Microsoft Azure we can say something called as Azure Functions, which is a similar offering. They allow the execution of functions in response to events, which abstracts away concerns about server provisioning and management. So this model offers unparalleled scalability, cost efficiency and agility. However, challenges like cold start latency and vendor lock-in, for example, if you are stuck with single AWS provider for longer period and you want to move out, then there will be problems without having a proper migration strategy between clouds. So that will require a very careful consideration. So the journey from bare metal servers to serverless functions, it represents actually a very remarkable evolution in the IT infrastructure. So each stage what it did, it addressed some specific challenges and brought about improvements in scalability, flexibility and efficiency. So the adoption of serverless computing also signals a very paradigm shift, emphasizing the importance of abstraction. Abstraction means uh, removing the overhead of manual intervention in maintaining the underneath platforms and automation in meeting the demands of modern applications. So as technology continues to advance, the evolution of IT infrastructure remains a dynamic and ongoing process, shaping the future of the cloud computing. So this is about how the shift took place to serverless offerings now. Also we'll see the evolution of serverless. So we should see like how evolution of serverless became again. So we can see here various terms like PaaS, which is PaaS, is already commonly said. Next we have the container orchestrator. We have IaaS, which is infrastructure as a service, and bare metal. So understanding these concepts is very crucial for navigating the modern tech world. So you should know where the tech came from actually. Instead of directly diving into that, we should know how the technology progressed from time to time. So bare metal. So imagine it has a computer has a physical entity. So this is what we call bare metal. Metal means a thing, a physical thing. So in the early days of computing, everything ran directly on these physical machines. So each server had its own operating system, applications, and dedicated resources. While straightforward, managing bare metal servers was often inefficient. It required manual intervention for tasks like scaling or maintenance, making the process very time consuming, resource intensive. So earlier we had roles like help desk technician and like system administrator and technical support teams who already like fix the servers manually. Now you can see all those roles are gone due to the they are there, but they are very minimal since most of the organizations are moving to uh, cloud premises. Next we have the IaaS, which is infrastructure as a service. So to address the limitations of bare metal, infrastructure as a service emerged. So think of IaaS as a virtualized playground. So instead of dealing with physical servers, infrastructure as a service provides virtual machines on demand. So users can quickly scale resources up or down based on their needs. So this model offers more flexibility and efficiency compared to bare metal. So as multiple VMs can coexist on a single physical server, making better use of available resources. This is a very good offering. Next we had the platform as a service. So as technology continued to evolve, the industry sought various ways to simplify application development and deployment. So now we enter the platform as a service. So in this scenario, what happened? Developers were provided with pre-configured platform to build, test and deploy applications without worrying about the underlying infrastructure. So platform as a service, what it does abstract away complexities, which enables developers to focus solely on writing the business code. This approach streamlines the development process. It also promoted the collaboration and it accelerated time to market for applications. So then we have this container orchestrators. So containers represent another layer of abstraction in the IT world. So imagine these as lightweight, portable boxes that encapsulate applications and their dependencies. So container orchestrators such as Kubernetes and Docker Swarm manage the deployment, scaling and operation of these containers. So they automate tasks like load balancing and ensure that applications run seamlessly across various environments. Containers and orchestrators have become instrumental in achieving consistency and efficiency in the modern software development. So, in wrapping up our exploration here, so understanding basics of bare metal, infrastructure as a service, platform as a service, and container orchestrators is very key to navigating the IT landscape. So, on top of all this, we have this enter serverless offering. So at its core, this serverless computing, what it did was it shifted the responsibility of infrastructure management from developers to cloud service providers like AWS, Google Cloud, and Microsoft Azure. Even Alibaba Cloud, we have IBM Cloud, any like private cloud vendor. So in a serverless architecture, what happened? Applications are broken down into the individual functions. So each was designed to perform the specific task. So these functions, often referred to as serverless functions or simply functions, are event triggered and execute in stateless environments. So cloud providers such as AWS Lambda, Azure Functions, and Google Cloud Functions automatically handle this scaling, deployment, and execution of these functions. So next we had traditional application models like monolithic application. Then we came into breaking down into the microservices, then make each microservices HA, which means highly available, then protect against regional outages. So after monolithic application, like it was the history of building the software applications. So after we came into microservices, what happened? There was explosion in number of containers or processes. So it's like cutting a big piece of cake into piece by piece. So you have many things to manage now. So you may have heard like the monolith word for first time, right? Monolith means like in it's like a single entity. You have may have heard like in history we can see monolithic stone in some geographical locations. We can see they mention something called as a monolithic stone, which is a single object you can say. So here in our case in IT, what we see a monolithic application. It's a traditional software architecture where all the components and modules are tightly integrated into a single unified code base. So in a monolithic architecture, what happens is the entire application, including the user interface, the business logic it has, and the data access layer is deployed as a single unit. So this approach contrasts with distributed systems, as all functionalities share the same code base and runtime environment. So for example, architecture components in user interface, we can have the UI is often tightly coupled with rest of the system. So user interfaces are typically built using technologies like HTML, CSS and JavaScript. Next, the business logic. So core functionality and business rules of the application are encapsulated within a single code base. So changes to the business logic may require modifying the entire monolith. Next comes the database. So monolithic applications typically use a single centralized database. So all data access operations are part of the monolith, simplifying the backend transaction management. So there were some advantages of them. So they were very simpler to develop and initially deploy. So the entire system is packaged and deployed as a single unit. Also, debugging and testing in a monolithic architecture, it was easier since all components shared the same runtime environment. Next, like in some cases, monolithic architecture were enabling faster development cycles, especially for small to medium sized projects. But it had come with its own set of challenges. So scaling monolithic applications was very challenging. So as the entire system must be replicated, even if only a specific component requires additional resources. Next, this maintaining and updating the monolithic applications was also very complex, as changes to one part of the code base may have unintended consequences on other components. Also, monolithic architectures limited the use of different technologies for different components, as they all share the same runtime environment. So, after we came into the advent of microservices architecture, so it's a very modern software approach, like modern software design approach, we can say, where the application is decomposed into small independent services that communicate through the well-defined APIs. So each microservice we have, like for example, we have this n number of boxes, right? So it is like splitting the main stone and cutting into smaller pieces. So each microservice is a standalone unit responsible for specific business capability. So these services can be developed, deployed, and scaled independently, promoting agility, scalability, and maintainability. So there are some architecture components for it. So it had microservices, it had the API gateway, which acts as a central entry point for clients to interact with the microservices. It managed the secure requests, routing them to the appropriate microservice. Next, we had some data storage services as well. So microservices can have their own dedicated databases, allowing them to choose the most suitable data storage technology for their specific needs. Next is the communication protocols. So microservices communicate through APIs, typically using lightweight protocols such as HTTP or REST, or messaging systems like RabbitMQ or Kafka. So it comes with awesome advantages actually. So microservices, what they do, they enable very fine-grained scalability. So it allows the individual services to scale independently based on the specific resource requirements. Next is the technology diversity it comes with. So each microservice can be developed using different technologies, allowing teams to choose the best tools for a specific functionality they are responsible for. Next is the continuous deployment. So microservices support continuous integration and continuous deployment, which is in modern terms called as CI/CD. So it enables faster release cycles and updates for enterprise applications. So since we already know each microservice is independent of each other, so failures in one service do not necessarily impact the entire system. So this promotes fault isolation and improves system resilience. Also, this microservices architecture facilitates team independence, as different teams can work on different microservices without affecting each other's work. But as they say, like greater power comes with greater responsibilities. So there are also greater challenges of this modern microservice architecture. So there's a huge complexity involved. So first is like managing a distributed system with numerous microservices introduces complexities in terms of deployment, monitoring, and overall system understanding. Also, there is a lot of communication overhead between teams as well. So, effective communication between microservices is very crucial, and improper communication patterns can lead to increased latency and complexity. So, data consistency is also another important parameter. So, operating and monitoring a microservices architecture, it requires additional tooling and infrastructure compared to monolithic applications. So this was about like a more of an overview we can say. So in conclusion, like both monolithic applications and microservice architectures have their places in the world of software development. So each offers distinct advantages and challenges. So monolithic architectures are suitable for simpler projects and scenarios where development speed is a priority. On the other hand, microservices architectures shine in complex, large scale applications where scalability, flexibility, and fault isolation are critical. So, the choice between these architectures depends on the specific requirements, scale, and nature of the project at hand. So, as technology continues to evolve, the software development landscape will see further innovations and adaptations in these architectural paradigms. So this is a small comparison box that we have. So it's a comparison of the different parameters like availability. So in traditional models like VMs and containers, we have at least 2 to 3 instances of everything. But here in serverless, there is no incremental infrastructure. So next we have the multi-region deployment. So here we have the one deployment per region, but here it is not specified. You can spin up any number of deployments. Next we have cover delta between short load spikes and valleys. So here we have almost 2 times of the average load, but here there is no specific thing. Next we have the example increment cost. So as per the instances and the regions as it scales, so the cost will be 8x, but here there is no sudden spike of cost. The incremental cost is 1x here. So these are some open source and openly like current available market of the serverless offerings. We have the Apache OpenWhisk, we have the AWS Lambda from Amazon Web Services, we have the Open Lambda, we have Fission Kubernetes, which is for containerized workloads and orchestration. We have the FN, we have the Google Functions from Google Cloud Platform, we have the Red Hat related function service, we have the IBM Cloud Functions. So these are the official logos as well. So just to have an overview, you should be very keen on observing what all trends are coming up in the market. Next we'll have introduction to serverless and the AWS Lambda. So as we already know, serverless architecture, it allows developers to build and run applications without the need to manage the servers. So AWS Lambda is a serverless computing service provided by AWS. So with AWS Lambda, you can run your code without provisioning or managing servers, paying only for the compute time it is consumed. So it's also pay as you go service, and the operational overhead is not there here as well. So where you are just putting your code and running the application. So next we need to understand the benefits of serverless architecture. The main thing is the scalability. So serverless architecture automatically scales based on demand, ensuring optimal performance. So based on the demand, like if the demand is very high, then the infrastructure beneath it will go accordingly, and if the demand is less, then according the resources will be provisioned. Next is cost effective. So it's a very cost efficient resource as well. So we need to pay here only for the compute time you actually use, eliminating the cost of idle resources. So there is no like if you just sit idle and application is not running, then there's no point to pay for the cloud vendor, right? So it's always good that only the compute time that you have spent that need to be paid. Next is the reduced operational overhead. So serverless architecture offloads server management and maintenance tasks for the cloud provider. So everything is managed in the backend by the cloud provider, for example AWS here. So you don't need to have a separate team for managing all the operational work that you have. So only your developers need to be focused on the application logic. So it's very important to understand how AWS Lambda works in the backend. So initially what it does, it allows us to run your code in response to events such as changes to data in an Amazon S3 bucket or a new message in a Amazon SNS topic. So next is you can write your code in multiple supported programming languages including Node.js, Python and Java. Then Lambda what it does, it automatically provisions and manages the compute resources required to run your code. So first in terms of the AWS Lambda architecture overall, so first what it comes is the function execution life cycle. So when a trigger event occurs, what AWS Lambda does is it initiates the execution life cycle of a function. So the process involves several key steps. Initially, the event source mapping happens. So events from various AWS services are mapped to Lambda functions. So this mapping determines which function will be invoked based on a type of event. Next is the function execution. So once triggered, Lambda executes the function in an isolated environment known as a container. So containers are ephemeral here and only exist for the duration of the function execution. Next is provision resources. So AWS Lambda automatically provisions the necessary compute resources for the function to run, ensuring optimal performance and scalability. So as we already discussed, it supports multiple environments as well. So you can choose runtime environment when responsible for executing the function's code. Also functions can access temporary storage space known as /temp, so which is unique to each invocation. So this space is very useful for handling the temporary data during function execution. So after execution what happens? Lambda returns the results to the calling service or client. So the function's output can be used to trigger subsequent actions or update other AWS resources. So in the backend what happens? AWS Lambda revolutionizes backend development by offering a serverless architecture that eliminates the complexities of infrastructure management. So its event-driven model, pay-as-you-go pricing, seamless integration with AWS services, make it a very versatile and efficient solution here. So there are some important use cases for AWS Lambda. So where it is used. So first is the real-time file processing. So Lambda can process files as they are uploaded to an S3 bucket, enabling real-time data analysis or transformation. So you can accordingly choose the event sources. For example, S3 events when files are uploaded, modified or deleted in an S3 bucket. S3 can be configured to generate events. So these events can include object created for new files, object modified for updates, or object removed for deletions. So Lambda can set up to automatically trigger in response to these S3 events. Next, if you have some Amazon DynamoDB streams, let's take an example. So if you are using DynamoDB, changes to the database can trigger events via DynamoDB streams. So Lambda can be configured to process these stream events, allowing real-time updates based on changes to the DynamoDB tables. So it also supports other event sources as well. So you can set up AWS Kinesis data streams, AWS Simple Notification Service, or any AWS CloudWatch events as well, depending on your specific use case. So setting up Lambda function is also pretty much easy. So you can create a new Lambda function in the AWS Management Console or using the AWS CLI as well. So we can define the function's runtime environment, specifying the programming language and resources needed for execution. So this is about real-time file processing. Next, it also has for web application backends. So here Lambda can serve as the backend for web applications, handling API requests and executing business logic. So it can also serve as a powerful backend solution for web applications, offering a serverless architecture. So since it operates on the event-driven model where functions are triggered in response to specific events, for web applications, what happens? Common events include HTTP requests or file uploads or database changes and more. So this event-driven nature aligns well with the dynamic interactions and data changes inherent in web applications. So for handling HTTP requests in web applications, Lambda is often integrated with Amazon API Gateway. So API Gateway serves as the front-end interface, routing requests to Lambda functions based on defined endpoints. So this combination enables the creation of serverless APIs for web applications. Also, it can help as a backend for mobile and web clients. So Lambda can serve as the backend. For web applications, Lambda functions can process requests from the front end, execute business logic, interact with database and return responses. So this seamless integration facilitates the development of robust and scalable web backends. So again, it also has integration with other services as well. So next is the IoT data processing, the third point. So Lambda can process and analyze data generated by IoT devices, enabling real-time decision making. So processing IoT data with AWS Lambda allows for a very scalable, real-time and serverless handling of data generated by IoT devices. So IoT devices are nothing but they are equipped with sensors or actuators which generate data. So this data is sent to an IoT message broker such as AWS IoT Core. So we have something called as AWS IoT Core in AWS, which is a managed service that enables secure communication between IoT devices and the AWS cloud. So it acts as a message broker, receiving and storing messages from devices. So next we have the IoT rules engine concept as well. So the AWS IoT rules engine is used to define rules that trigger actions based on incoming IoT messages. So when a predefined condition is met as specified in the IoT rule, the rule triggers the execution of a Lambda function. Also it has integration with AWS Lambda as well. So IoT rules engine can get accustomed to AWS Lambda here. Also, as you know, it is used for data processing. Then it also supports the real-time processing. So Lambda functions are designed to execute in near real time. So as IoT events occur, Lambda functions respond almost instantly, allowing for real-time processing of data. So also the event payload is important here. So the IoT message payload, which contains data from the devices, is passed on as an input to the Lambda function. So the function can extract relevant information from the payload for further processing here. Also inside the Lambda function, developers can implement custom logic for transforming the raw IoT data into a desired format. So this may include filtering data, aggregating values, or performing complex analytics depending on the application requirements. So also AWS IoT, it supports the publish subscribe, which in layman terms called as pub sub communication model. So multiple Lambda functions or other AWS services can subscribe to the same IoT topic. So this enables the parallel processing of IoT data by different functions. So next we have the error handling and retrace. So Lambda functions can include error handling mechanisms to manage potential issues during data processing. So AWS IoT automatically retrace the execution of a Lambda function if it fails, ensuring resilience in the face of transient errors. So this is about use cases. Next we have the key features. As you already know, it's a event driven architecture. So Lambda functions are triggered by events and can be connected to various AWS services, allowing for seamless integration. Next we have the auto scaling feature. So Lambda automatically scales to handle the incoming workload, ensuring high availability and performance. Also it has a very easy deployment and management feature. So deploying functions is very straightforward using AWS Management Console or CLI. Also pricing and cost optimization is very important. So AWS Lambda offers a pay per use pricing model where you only pay for compute time used by your functions. Optimizing costs can be achieved by tuning the memory allocated to your functions as it affects the overall execution time and cost. AWS provides tools like AWS Cost Explorer and AWS budgets to monitor and manage your Lambda costs effectively. So the primary factor influencing the Lambda pricing is the duration of function execution, so which is measured in milliseconds. So users here are billed for the total time their code is running, rounded up to the nearest 100 milliseconds. So this means that even if a function runs for only a few milliseconds, the user is billed for the entire 100 millisecond block. So Lambda functions are also allocated a specific amount of memory which is in gigabytes when they run. So users can configure the amount of memory for a function ranging from 128 megabytes to 3008 megabytes. The chosen memory size also determines the amount of CPU and other resources allocated to the function. So Lambda pricing is very granular and based on the actual resources consumed during execution. So users are billed per GB second where the total cost is calculated by multiplying the function's memory size by the duration of its execution in seconds. So it also provides a free tier for Lambda offering a certain amount of free compute time and memory each month. So this allows users to experiment with Lambda functions and experience serverless computing at no cost within specified usage limits. So it has per invocation pricing. So in addition to the compute time and memory, there is a per invocation cost associated with Lambda functions. So users are billed for each time their function is triggered, whether it's in response to an event, an API gateway request, or any other type of invocation. So there are also data transfer costs involved. Lambda functions may interact with other AWS services or external resources, leading to data transfer costs. For example, if a function reads from or writes to an Amazon S3 bucket located in a different AWS region, data transfer costs apply there as well. So consider a Lambda function with a memory size of 512 MB that runs for 300 milliseconds. So the user would be billed for 512 MB multiplied by 0.3 seconds, resulting in the total GB seconds consumed. So the actual cost is then calculated based on the GB seconds consumed and any additional costs related to data transfer or invocations are added later on. So this was about pricing. Next is the security and compliance. So AWS Lambda provides built-in security features such as IAM roles and policies to control access to your functions and resources. So you can encrypt data at rest and in transit using AWS Key Management Service for enhanced security. So AWS Lambda is compliant with various industry standards, including HIPAA, PCI DSS, and ISO 27001, enabling you to build secure and compliant applications. So as you already know, IAM is very central to Lambda's security model. IAM enables users to define roles and policies, controlling who can create, modify, and execute Lambda functions. So fine-grained permissions ensure the principle of least privilege, limiting access to only the necessary resources and actions. Next we have something called execution roles. So Lambda functions run within an execution role. So which defines the permissions the function has to access other AWS resources. This role is associated with an IAM role, allowing developers to control and restrict the actions a function can perform. So this ensures that Lambda functions only have the required level of access. So Lambda functions can also be integrated with virtual private clouds to isolate them within a private network. So this allows users to control the network configuration, including subnets and security groups, enhancing the security posture of Lambda functions by restricting access. So Lambda functions can securely communicate with other AWS services using encrypted connections, ensuring data integrity and confidentiality. So functions can leverage AWS key management service as well for encrypting data at rest, including the storage of function code and any associated environment variables. So it's also compliant with industry standards. Also there are some other industry standards such as SOC2 and SOC3 and more. So these certifications what they do, they demonstrate AWS's commitment to maintaining a secure platform. Also it has integration with AWS CloudWatch. So it is the logging and auditing Lambda functions. CloudWatch logs capture function output, errors and other events, allowing developers to monitor and analyze the behavior of functions. Additionally, CloudWatch metrics provide insights into function performance, aiding in troubleshooting and optimization. So next we have the monitoring and debugging. So it already has integration with AWS CloudWatch. So we can enable detailed CloudWatch logs for the functions to assist in debugging and troubleshooting. Next, AWS X-Ray can also be used to gain end-to-end visibility into the execution of serverless platforms, identifying performance bottlenecks and optimizing them. So this is about the monitoring capabilities along with Lambda. Next we have the integration with other AWS services. So AWS Lambda integrates seamlessly with various AWS services such as Amazon S3, Amazon DynamoDB, and Amazon API Gateway. So this integration enables you to build serverless applications with a wide range of functionality and leverage power of other services. The tight integration with AWS services simplifies development and reduces the complexity of managing infrastructure. So this Lambda is also a very core component of the serverless offerings along with Fargate. So it has like along with EC2 and some other prominent providers services. This also has a wide integration with all the services. So now we'll see the best practices for AWS Lambda. So initially it says keep functions small and focused. So break down your application into smaller functions for easier testing, maintenance, and scaling. Then use environment variables. So store configuration values in environment variables to separate them from your code and make them easily configurable. Next, implement error handling and retries. So handle errors gracefully and implement retries to enhance the reliability of your functions. So it mostly speaks about the function design. So design functions to have a single responsibility. So this follows the microservice architecture, making functions modular and easier to manage. So also we need to keep the functions stateless to allow for better scaling and reduce of complexity. So idempotency is also important. So ensure that functions are idempotent, meaning repeated invocations with the same input yield the same result. So this is crucial for handling retries and ensuring data consistency. So resource allocation also should be carefully done, like adjusting the memory allocation for Lambda functions should be based on the resource requirements. So right sizing also helps optimize performance and cost here. So we need to, there will be some chances where may be some cold starts as well. So we need to have some warm up strategies there. So we can mitigate cold start latencies by implementing warm up strategies. So periodically invoking functions or using services like AWS Lambda provisioned concurrency can keep functions warm and reduce cold start times. So error handling is also there. So we can use AWS CloudWatch logs for logging. So it will implement comprehensive logging to capture errors, warnings, and other relevant information for debugging and monitoring. So we have something called as DLQs, which is called as dead letter queues. So we can configure dead letter queues to capture and analyze failed invocations. So DLQs allow you to investigate and retry failed executions. So security is also important. So IAM rules need to be specified accordingly. There should be environment variables. So we should need store sensitive information such as API keys or any database credentials if you are having. They should be stored using environment variables. Also encryption should be enabled for data in transit and at rest. So you can use AWS key management service for encryption of environment variables and data storage. So integrating AWS X-ray is also good for distributed tracing and performance monitoring. So X-ray helps identify bottlenecks and visualize the flow of requests as well. So versioning is also important. So version control should be done. You can use AWS Lambda versions and aliases to manage changes and updates systematically. So this enables rollback to a previous version if needed. Also we can leverage the use of blue-green deployments. So we can implement blue-green deployments using aliases to reduce the downtime during updates. So this was about some best practices. So we'll discuss the limitations of AWS Lambda, like what are the limitations it has. So first is the execution time limits. So Lambda functions have a maximum execution time limit of 15 minutes and should be designed accordingly. Next we have the cold start latency. The first invocation of a function after a period of inactivity may experience a short delay due to provisioning of resources. So we saw why cold start latency happens in the previous slide. So next is temporary storage limitations. So Lambda provides only limited temporary storage space within the execution environment. Actually, this execution time limit it varies according to the runtime. So for example, the maximum execution duration for single invocation is 15 minutes for Python, Ruby and Node.js and 5 minutes for other runtimes. So long running tasks may be needed to be broken down or handled differently here. So also AWS Lambda here it allows for allocating memory to functions from 128 MB to 3008 MB here. So however amount of CPU and network resources allocated scales with the chosen memory size. So high performance computing requirements may be better suited for other AWS services like EC2. So regarding this temporary storage limitations, it has access to limited amount of temporary storage space as already saw, like the slash TMP which we saw during execution. So this space is ephemeral and has a size limit which may impact certain use cases that require extensive or persistent local storage. So Lambda functions experience a delay known as cold start. So you have seen vehicles, right? For if you have make them stand for a long period of time in cold environments, the vehicle won't start. So you need to do that cold start. So in terms of Lambda, it is also this delay is called as cold start only. So when they are invoked for the first time or after a period of long inactivity. So the time it takes to initialize a new execution environment can introduce latency, impacting real time or latency sensitive applications. So Lambda functions are mostly designed to be stateless and they do not provide any persistent storage between invocations. So this may require external storage solutions such as databases for S3 for managing application state. Also, the deployment package size for Lambda functions, including code and dependencies, also has a limit. For example, the maximum size for deployment packages is 50 MB for AWS Lambda Edge functions and 250 MB for other functions. Also, there is some environmental size variables size limit is there, so that can be set for Lambda functions. So if an application requires extensive configuration or sensitive information, developers should consider alternative approaches for managing such data. So this was about some limitations that we discussed. Next is some case studies. First is the serverless image processing. So we can use AWS Lambda to automatically resize and optimize images uploaded to an S3 bucket. Next, we can trigger the Lambda function whenever a new image is uploaded and generate multiple resized versions. So this serverless approach eliminates the need for manual resizing and reduces storage cost by storing only the required versions. So I think S3 integration is pretty much in case of all like file handling operations with AWS Lambda. So next we have the real-time data processing. As we already said, it has better integration with IoT devices using IoT Core. Next we can trigger Lambda functions based on incoming data events and perform real-time analytics. Also, this serverless architecture enables near real-time processing with low latency and high scalability. So these IoT devices can be integrated for these real-time updates. Also, chatbot integration is also possible. So we can develop a chatbot using AWS Lambda as the backend to handle user queries and perform necessary actions. So we can integrate the Lambda functions with seamless with messaging platforms like Facebook Messenger or Slack for seamless user interaction. Serverless approach provides flexibility and scalability to handle varying chatbot loads. So you may have seen a Amazon chatbot, right? If you have purchased an order and you're waiting for the customer chat, so automatically a bot actually asks couple of questions before you move ahead and chat with the real person. So similarly, this Lambda also can help us in creation of chatbots. So how it fares with other serverless providers? So we need to compare this with other serverless providers available in the market. So AWS Lambda is one of the leading serverless platforms, but alternatives like Microsoft Azure Functions and Google Cloud Functions also exist. So due to the first more advantage from Amazon, because since it was the first cloud provider in the world, so AWS Lambda is still the leading serverless platform because organizations didn't had a choice at that time to play around. So they stick to AWS Lambda and still it is in the leading phase. So considering factors like language support, integration options and pricing when choosing a serverless provider. So when you are choosing among a given set of available options like Azure functions and Google Cloud functions, we need to first see like what platform and language our application code supports and what are the different integration options. For example, if it is a container based or a managed serverless based, or it's just hosted on a EC2 instances. And also we need to just check the per GB second pricing for all the services as well, and we need to calculate the TCO, which is the total cost of ownership, and then accordingly choose the best provider. Also, SLA is also important here. So service level agreements of the serverless offerings must also be compared so that you know how much downtime is going to be faced in a particular calendar year. Next is each provider offers unique features and capabilities. So evaluate your specific requirements before making a decision. So it's always helpful to take help of a cloud architect working in multiple cloud providers so that he or she can consult you on taking a better decision. So how to get started with AWS Lambda? So it's very simple. We just need to have an AWS account, or we need to sign up if you don't have. Then again, familiarize yourself with the AWS Lambda documentation and tutorials available on AWS website. So there are some already hands-on sessions by AWS platform, and documentation is also there. So it's always a good practice to go to the documentations and read the white papers of different use cases, because most of the queries you'll only understand because everything will not be provided via the console. So then we can start experimenting with simple Lambda functions and gradually explore more advanced use cases. So conclusion is serverless architecture and AWS Lambda offer numerous benefits, including scalability, cost efficiency, and reduced operational overhead. So AWS Lambda is a very powerful serverless computing service provided by Amazon Web Services. With its seamless integration with other AWS services and rich features, AWS Lambda enables developers to build highly scalable and flexible applications. So this is a wonderful platform by AWS. So we'll see in the hands-on session of creating a simple uh, Lambda function. So I'm already in the console now. So in this hands-on session, what we'll do, we'll write a node.js Lambda function that checks a URL called www.amazon.com and returns the status code that signifies if the website is up and running or down. So during this lab, you'll have the opportunity to explore the Lambda console, function code, execution roles, test events, and execution results. So AWS Lambda allows us to write concise functions and only worry about the code here. So since Lambda is serverless, AWS manages the underlying infrastructure for us here. So we'll need to search the Lambda first from the console here. So I'll hit Lambda. So this is the first one with this symbol, Lambda symbol. It says run code without thinking about servers. So literally it is like that. So here we have the dashboard here. In the left side it says dashboard, applications, functions. So by default you are taken to the functions page. So I'll just delete a function which is already existing. Under actions I'll delete it so that we don't get confused. So what we'll do, we'll create a function. So here we'll select the author from scratch. So we'll give the function name something kind of HOL URL checker. Just a random name, you can give any name based on your familiarity. So runtime I will search as something, I'll search the node.js 16.x since we have the code accordingly. Then we'll leave the architecture as it is. So instruction set architecture for our function code will be /86 underscore 64. So next we need to open this change default execution role. So the execution role, what we'll go ahead with the default one, which is a create new role with basic Lambda permissions. So it gives a warning which says a role creation may take a few minutes. So please do not delete the role or edit the trust or permission policies in this role. So be patient and wait for the process to be completed accordingly. So now I'll go ahead and create the function. So it says successfully created the function HOL URL checker. Now it says you can now change its code and configuration to invoke your function with a test event. So choose test, it says. So if we scroll down here, it says the code editor does not support the .NET or C# powerful runtime. So we'll go with the test. So here you can see the code source available here. So under this, so since we don't have any, so we'll paste it from the sample GitHub repository. So I'm creating a new file called index.js. So and under this thing, so now I'll just go ahead and deploy it. So it successfully updated the function to HORL checker. So actually this code is very simple. So what this code does is just checks the URL, this www.amazon.com, and checks if the URL is up or not, whether it's working or not. That's it. So what we need to do now, we'll now create a test event here and to execute this lambda. So I'll go under test. So I'll go ahead and configure test event. So I'll create a new event here. So event name. So we'll name this as my first event, and we'll leave the event sharing settings as private. So this is a template option. So we'll see there are a couple of templates available. We have app sync, batch submit job, tons of events actually. So but the common is hello world. We'll go with hello world. So event JSON is required actually. We'll not feed the key value information here, but just that it should be existing for as a event JSON here. So we'll leave it as it is and just click on save here. So the test event, my first event, was successfully saved. So now what we'll do, I'll just hit the test. So we got this error. So it's a runtime import module error. So also if you want to see any metrics or CloudWatch logs related to Lambda, then you can come here and see any relevant for any errors or any logs you want to see. Yeah, this was about all of the hands-on session. So in conclusion, we saw like what AWS Lambda and serverless offerings are and what are the benefits and features. And we also saw how to create a simple Lambda function using the AWS console here. So in the next session, we'll be seeing how AWS Cloud Automation works using Terraform and CloudFormation. So see you in the next session, and thank you for attending the session. Bye everyone.